Thanks everyone for coming to the first lecture of this class, Introduction to Diffusion Models. So in this lecture, I'll talk a little bit first about applications of diffusion models, just to show you some potential applications and some nice images and videos and get you guys interested in diffusion models. And then we go over course logistics and such as homework and projects. And then we go into the meat of today's lecture, which is what are diffusion models? How do we train them and how do we sample them? And for this lecture, we introduce them from a more practical perspective, where we actually show code and talk about practical considerations. So first, let's introduce you to the things that diffusion models can do. All right, so I guess most of you should know, first encounter diffusion models through stable diffusion. So this is text-to-image generation, where you're given a text prompt, and this model can generate a very high-resolution image that follows the text prompt. It can even generate images containing text that you specified through the prompt. So Stable Diffusion really brought this capability to the general public. And that's also when I first learned about diffusion models. This is about 2 years ago. And not only that, these diffusion models let you control what's being generated, not only through text, but also through other modalities such as images. In this example, you see that you're given a very simple sketch of what you want the image to be. It kind of specifies the colors and some very simple cartoonish sketch. And the model is able to generate very highly detailed and refined images that follows the same kind of color scheme and have similar objects that's in the sketch. So this I find really, really magical the first time I see it. All right, so not only this, you can see that this gives kind of a coarse-grained control where you don't exactly follow the same outlines. But people have done, you can do even better. This is called control net. So this takes a pre-trained diffusion model, and then it kind of fine-tunes it to follow very precise guidelines, such as this. You can input the canny edges that you want the generated image to have, and it's able to very precisely follow the same edges, although with different styles. Right, so you can see that the deer in this image is basically the same, but you can choose the styles based on different text prompts. And not only images, edges, you can have different other modalities such as human poses. You can see that these people basically have the same pose. So another application of diffusion models is through image editing and composition. So here, you're given a few input images of a particular dog. After a small amount of training or fine-tuning, you can teach the diffusion model what this dog is, and you're able to generate images that contain the same dog, but in different poses and in different settings. Right. Going beyond image editing and composition, people have also used diffusion as a prior for certain image restoration tasks, such as super resolution, where you want to turn a very low resolution image to a high resolution one. And inpainting, where you blur out parts or block out parts of images and ask the diffusion model to fill in these parts. Also colorization, we're given a black and white image and you want to fill in the colors. And the reason the diffusion model is able to do this is because it kind of understands what this, for example, what colors these different parts of the image should have from its training data. Or it understands what to fill in here. This is kind of like a lion. And it's able to do this very well. All right. Not only that, here's another very fun application of diffusion models, where you're able to generate visual illusions. So for example, you see here this image looks like a penguin from one way and a giraffe from the other way. And you can see that in certain cases, you can make images that look like one text prompt from one angle and a different text prompt from a different angle. You can even cut these images up and paste them together to form two different objects. In fact, in one of the homeworks, you'll be building one of these illusions, like from scratch, using these diffusion models. All right. Not only, so far I've only shown you image generation, but diffusion models can do more than image generation. It can also do audio generation. So one of the earliest applications was to simply generate an image, which is the spectrogram of an audio form. So it's an image that you can turn back into an audio waveform. And people have also refined on that to generate different, create more detailed models that generate audio music from different text prompts. So right now the kind of frontier research domain for diffusion models is video generation. You see that here you're given like a text prompt, and then it's able to follow the text prompt and generate very detailed, although not very long, videos, and it has very nice kind of consistency and physics based on what is learned from training data. So these are all quite impressive. Right. In a slightly different domain, like it's talk about novel view synthesis, where you're given an input image, given the camera angle, and it's able to rotate the camera and generate a different image of the same object from a different camera angle. So it kind of, for example, here, like it takes in an image of a drum set, and it kind of is able to rotate the view of the drum set. This is because this is done through pre-trained diffusion models, fine-tuned on like different 3D objects. So this kind of makes you think, like, can you use diffusion models to generate 3D objects? And the answer, of course, is yes. This is one way you can use diffusion models to generate like different 3D objects. And here are some examples of 3D shape generation. The left one is the very first 3D shape generator called Diffusion, and the right one is like a more refined version after a year or two of research. So it's able to like generate basically meshes or 3D representations of shapes. All right. And here's one newer application which I find very impressive, where it's able to basically simulate a game engine, right? So what it takes as input is your control inputs, like you're taking in like you're basically putting in keyboard actions, and it's able to generate like or predict what's going to happen in this game. If, for example, this is like Doom. So it's actually able to simulate this game to a very high extent. Like even keeps tracks of your ammo and health by just generating like images or videos in this case. So it's able to like quite like to high fidelity generate simulate this game. And moving to like a new different domain is like protein synthesis, right? This is where you want to generate, instead of images or videos, you want to generate actual molecules and that are proteins. And one application or one important question people want to answer, like to solve in this case, is can you generate proteins that fit like certain binds to different proteins? And this is kind of like image inpainting. And there's like been works like here, for example, RF diffusion that has been quite influential and successful in this regime. And another like application here is imitation learning and robotics, where instead of where the goal is to predict a trajectory or predict the action of this robot given input images as well as sensor data. So from this, and it's learned, the training data, of course, is trying to do imitation learning, which is trying to mimic, given demonstrations, try to learn a task from like multiple demonstrations. So you can see that it's able to do a task like picking up a mug and flipping it upside down, and as well as like different, like say folding clothes, doing laundry. And what's very impressive about this is that this people have found that this like these policies learned from using diffusion models are quite robust to like different perturbations, and also work very well for these kind of deformable objects such as clothes. And this, so now we've seen many applications of diffusion models. I'll talk more about what you expect in this class and like what you get to learn in this class. So for a course outline, right? So we're going to have 6 lectures. So the first lecture is right now, where we talk about the introduction to diffusion models, and then the next lecture will be more about like interpretations of diffusion models and different perspectives. And then we'll talk more about conditioning and how to guide diffusion models, followed by more advanced applications such as like 3D generation. And then we'll talk more about how diffusion models generalize, and do they generalize, followed by a guest lecture, which more information will come soon. So there are 6 lectures. And here are the core staff, and Chris is here, so I'm Chenyang, and Chris is here, and you see more of the other like core staff who will give lectures in the next few days. As for logistics, well, we have the lectures. These lectures will be recorded as well as posted on the webpage. And here's the website, if you haven't seen it yet. All the materials such as homework and lectures will be posted here. And we also have a piazza, which we use as a discussion forums if you want to do homework. We'll also aim to have some office hours right before the homework is due. And if you have any questions about all of these, like feel free to post on Piazza or send us an email. If you haven't joined the mailing list yet, this is the mailing list. We'll periodically add people from Canvas. All right. As for grading, for people who want to take this class for credit, grading will be like pass-fail. And it consists of 3 components. First is attendance and participation. We'll track this by basically sending out a survey after each class, and then asking you to fill out the survey. If you fill out the survey, we give you the attendance credit. So for those who are taking it remotely, you can also watch the videos online and then fill out the survey. As for problem sets, we have 2 problem sets. First one will be released today. Next one released on Friday. It'll be due in like 3 or 4 days. And really the aim of this problem set is to give you a more hands-on experience with diffusion models. And the grading will be very coarse, like it will just be based on completion. If you make reasonable effort into completing the problem sets, you get full credit. As well as a mini project, which you can choose to do. So if you want to take this course for credit, you can see that based on the grading scheme, if you attend all the lectures and do all the problem sets, the mini project is optional. And you can also choose your own adventure by choosing which parts to complete. So you just need 18 points and above to get credit for the class. Is there any questions about logistics and grading? All right. So if not, then we'll go more into a deep dive about what are diffusion models and how do you train them and how do you sample from them. Right. So in a nutshell, right, diffusion models are actually, the name comes from diffusion processes. which, for example, Brownian motion, where you take a particle and keep adding Gaussian noise to it over time. You can see that if you start at 0, this process kind of evolves over time, and it's kind of like a random walk. So of course, this is in one dimension. You can do this for higher dimensional data, such as images, where you add independent noise to each pixel, one at a time. So this is kind of known as the forward process. By adding noise to data, you kind of transform the data, which is here in the image, to pure noise. And what diffusion models do is they try to learn the reverse process. They try to recover the data from noise. So for example, you start with the complete noise image, or the complete, and tries to predict a slightly less noisy version. And then it keeps on doing this until, in an iterative manner, until you get the clean image in the end. So this is kind of the high-level overview of what diffusion models are doing. And to be more concrete, right? Let's take a look at how diffusion models are exactly trained. So how do you train a diffusion model? So you start with a sample, which we call X0, from your data manifold, which could be images, could be like molecules, could be anything. And you take this clean data, you choose a noise level. How do we choose this? We'll talk about it more later. And then we choose a noise vector, which kind of, you can think of it as a direction, right? So you choose the clean data at noise level and the noise direction, and add the noise to the clean data. That's how you get the noisy version of the data. And what the diffusion models try to do is to try to predict the kind of the direction of the noise, given the noisy input, as well as the noise level. This is quite important. It takes in both the noisy input and the noise level, and it tries to predict epsilon, which in this case is like the noise direction, by minimizing some square loss. It's kind of, you can think of it as a supervised learning problem, where you're trying to predict the noise direction from the noisy image or noisy data. So how do you sample these three quantities? X0 is usually sampled uniformly at random from the training data, or by shuffling data and taking it in batches. The sigma is the noise schedule, which we will talk more about later. It's sampled from this noise level is sampled from the noise schedule. And the noise direction is simply sampled as an isotropic Gaussian, IID Gaussian in each component. So are there any questions about how this is trained, and any questions so far? All right. So if not, I'll go more into the details of like how these quantities are chosen, and I'll show you an example of training a simple diffusion model. So first, we'll talk about the noise schedule. Like, how do you pick the noise levels for adding to the clean data? So in practice, right, these noise levels can range from really small to really large. Like small as in 0.01 to large as in 100. If you think about as comparison, the magnitude of the data is about 1. So the noise can be much smaller as well as much larger than the magnitude of the data. And this noise levels are usually sampled from a discrete noise schedule. What the noise schedule is basically a list of different noise level. Here, sigma 1 could be 0.01, sigma 1000 could be like 100. And they're usually visualized on the plot here, where you have this basically a function where a sample are uniformly random t, and then this value here will be the noise level that you use. If you notice that this y-axis here is usually on the log scale, it's because of these very large range of noise levels that we have. We would usually view them on the log scale. So we use this coordinate lambda, which is basically the log of this noise level, or log of. We can also think of it as the log of signal to noise ratio. And this sampling procedure can actually be visualized here as a sampling from a distribution on this lambda, which is the signal to noise ratio. We're sampling from this 1,000 values. Could be also thought as like sampling from a predefined distribution. And these are known as different training noise schedules. So the noise levels used in training. If you notice here, right, it tends to focus this distribution tends to focus more on certain noise levels. In particular, noise levels that are not too big and not too small. And this is by design. And usually these noise schedules are picked based on what kind of data you have. You might need to change the noise schedule if you want to train a diffusion model on a very different modality of data. So here, so basically this is how you pick the noise. So to make things more concrete, let's try to train a diffusion model on basically a toy model. So we start with this 2D spiral data set. So basically our data just consists of points on the spiral. It's a very simple data set. It has, it's a two-dimensional data set, basically the x and y coordinates of these points. And you can add noise, different levels of noise, which you can see will kind of distort the spiral into basically a uniform Gaussian distribution. And this will be one of the inputs to the model. As for the other input to the model, you want to add the noise level. The model needs to know what level of noise we're adding. And to do this, we take basically we embed the noise level into another 2D vector. And we use these two, concatenate them together as inputs to our model. And our model here, because it's a toy model, it's basically a very simple deep neural network. It's called a multi-layer perceptron, which consists of linear layers followed by non-linearities. And this will predict the noise that is added to these data points. So in Python code, it basically just looks like this. You can take a look at this later, but this basically just implements this architecture that's shown in the diagram. So this would be the model we use to train for the 2D spiral data set. All right, so here we've shown a very simple architecture, but what are other more commonly used architectures that's, if you want to go beyond this toy model into more complex, say, image data sets? Here I just show two different architectures that are commonly used in practice. The first one is based on convolutional layers called a convolutional U-net. This might look very complicated, but I need to focus on this outline here. Basically, the input is kind of put through a series of layers that decrease the physical dimensions of these inputs. So basically from like say 64 by 64 to like 8 by 8. But of course it also increases the number of channels. And then there's the decoder part that kind of does the reverse. That increases the number of physical dimensions but decreases the number of channels. So, and these are connected by skip layers as well as conditioned by the current noise level. So this is the usually this is called U-net, and usually I think at first it was developed for image segmentation, but people have repurposed them for diffusion models, and this is the most commonly used architecture for image models. Another different, more recent architecture is based on transformers. If you've heard of this before, this is what's being used in large language models. But this is instead applied to images. So what happens is that you take an image, you break it down into different patches, and then you input the patches to a neural network to get different patch embeddings. And you basically take a transformer block that takes in these patches and then keeps on putting them through transformer blocks, conditioned by noise levels. So both of these architectures have the same inputs and outputs, which is the noisy image and the noise level, and it tries to predict what direction of noise is in the image. And these have different pros and cons, but I won't go deeper into them for now. Yeah, just to let you know that these are some of the more commonly used. Yes?
Question about the previous couple of slides. So what's the intention behind putting the loss on noise as opposed to just doing like a reconstructed loss?
Okay, so the question is, why do we put the loss on the noise, which use the square loss on noise rather than reconstruction loss? Yes, it's a very good question because there's multiple things you can predict. You can predict the noise. You can also predict the clean image. Both things actually work. Like you can build diffusion models predicting different things. You can even predict the difference of the noise and the clean image. And if you do that, you get something that people refer to as flow matching. So this is there's a variety of different ways to modify the loss. And for now, I'll focus on the first thing people have tried, which is predicting the noise. But we'll go more about predicting different quantities later. All right, so let's go back to the toy model. So recall that we had this toy data set and a very simple multi-layer perceptron. So what happens if we train this toy model? So here's the training code, which basically implements the loss function we described just now. You can see that this is just a loss function that takes between the noisy data and the clean data. And you can train it for a few minutes, and then you get the loss function kind of plateaus. And what do you actually get? Let's kind of visualize what we actually get. We try to use this learned denoiser to predict the clean data at different noise levels. So here, this is a very small noise level, this is a medium noise level, and this is where the noise level is large. And here we're starting at different points in this 2D grid and asking it to predict the clean data. And what do we get? So this arrow kind of corresponds to the prediction, predicted x0 for different points, say x sigma. So you can immediately see it predicts very different things given different noise levels. So at large noise levels, the predictions all tend to be towards the center of the data set. It tends to predict the mean of the data. And towards at smaller noise levels, you can see a spiral shape sort of starting to form. And at very small noise levels, it kind of predicts the points on the spiral itself. Although not exactly because if you look at these points in between, it doesn't actually predict the points exactly on the spiral. You have to be very close to the spiral for the predictions to be accurate in this case. So this is the kind of empirical behavior of what happens when you train this model. And now the question is what did the model actually learn, and how do we reconstruct or generate samples from this toy data set? Because we see that we cannot directly just use the model to predict the data. At high noise levels, you just basically get the mean of the data. You have to kind of sample it in a different way. But first, let's talk about what did the model learn. Okay. So I'll briefly go through this notion of the ideal denoiser, which is a denoiser that you can derive by essentially doing a deconvolution, like deriving the deconvolution, like by using some Bayes law and like other calculations, you're able to basically write down a closed form solution of this denoiser, which kind of looks like this, given like a finite data set. And for our purposes right now, we just say that this ideal denoiser is basically what you get if you minimize this loss function exactly. So let's take a look at a different interpretation of the ideal denoiser to kind of get an intuition of what's happening previously. Like, why did this learned model predict different things at different noise levels? All right. So we'll talk more about a distance function. So first, we define a distance function to be basically a distance to these data sets. And something interesting is that the gradient of a distance function is basically projects onto a data set. So here you can see that if you take a point, there's data set here is this outline in black. If you take a point outside of this data set and compute the gradient of a distance function, it kind of projects onto the surface. This is nice, but one problem is that the distance function is not smooth. There are many ways to smooth the distance function, and one of them is to use a soft min instead of a min here. So if you smooth the distance function this way, it turns out there's a very nice connection between this and this ideal denoiser. And in fact, the gradient of this smooth distance function is exactly what the ideal denoiser predicts. So you can think of the ideal denoiser, which is what this model is diffusion model is trying to learn. It's basically trying to predict the gradient of a smooth distance function. So what happens if you try to smooth the distance function with a larger smoothing parameter? The prediction will be inside this kind of surface. And if you increase the smoothing parameter to be very large, the prediction will be close to the mean of the data. So this is kind of what is happening here when you're learning this denoiser. You're trying to predict the mean you're trying to smooth this distance function and smooth the projection to this data set. And that's what's causing it to predict more and more towards the mean of the data as you add larger and larger levels of noise. So this is kind of one way that I think about what's happening when you try to predict the X0 given a noisy data with larger and larger levels of noise. Okay, so now we kind of have an idea of what this model learns, right? How do we sample from diffusion models? We know that you cannot just call the diffusion model once with a large noise level, because it will just return the mean of the data. You have to call it multiple times. So here, let's just call the predicted clean data to be at a certain noise level to be X0 hat. And in a nutshell, what's happening here is that you want to, at xt, right? If you predict X0 hat, you get close to the mean of the data, but you don't want to move all the way to X0 hat. You want to move a small distance, a small amount, and then you want to call the denoiser with a smaller amount of noise. So this is kind of taking an iterative approach and slowly reducing the noise level, taking multiple steps to get closer and closer to the data manifold. So this is basically what sampling algorithms of diffusion models do. they take multiple steps, like slowly getting closer and closer to the data manifold. And here, where the step size is just determined by the difference in noise levels. All right, question?
Is the fact that you need to do this sampling only because of like the practical limitations of like the diffusion model not being an ideal denoiser?
No. So the question is, even if the diffusion model is ideal denoiser, can you sample in like one step? It turns out that you cannot. It's very hard because if you take because you see for the ideal denoiser at large levels, it will also predict the mean of the data. There are, however, other ways to like make diffusion models sample from one step or two steps, but that's known as consistency models. But I think that's a topic for later. And I think one of the advantages of diffusion model is this kind of multi-scale nature in which it takes multiple steps, and this makes it more tolerant to like noise in the sampling. It also makes it easier to train. It kind of breaks the very difficult problem of generating the data from nothing into multiple smaller but easier to learn steps, which is denoise a little bit at a time. So I think that's one reason why diffusion models has been so successful. And so here we presented a simple sampling algorithm. Here, this is known as DDIM. How do we actually implement it, right? So this is just an algorithm we showed just now. Very simple step. Here you call the denoiser, and then you take a step, and then you repeat for n times. And the code to implement this is also very simple. It implements this algorithm, and this is what happens when you implement this algorithm using the learned denoiser that we trained just now. So the red lines here basically represents this xt, but you're starting at different points. Like the start points are all outside, and this animation kind of shows you the trajectory of the sampling, sampling trajectory that these points take to, and you see this trajectory is mainly end on the data set. So you're getting back like samples. And let me watch a few more times. Yeah, so this is a good way to visualize what happens for different samplers. So we'll talk a bit more about different samplers later. So so this is a very simple deterministic sampler, but there's many samplers out there. And one thing you might have seen is probabilistic sampling, where you're adding noise between sampling steps. And how exactly do you add the noise? So what happens here is that you're taking a step that is smaller than what you would take in deterministic sampling, and then you're adding some noise to this. And there's a very specific way that, like between sigma t prime and eta, that you can choose. It basically balances out the noise levels in expectation. And so with this probabilistic update, there's basically one parameter you can choose, which is mu here, which kind of determines how much noise you're adding. You can add a lot of noise or just a tiny bit of noise. So this kind of provides a way to interpolate between the deterministic and probabilistic updates. And here's the visualization of what happens when you start adding noise to it. So the black lines here are the deterministic trajectories that you've seen before. The red lines is what happens when you're adding a little bit of noise. If you increase the noise levels, you can see that it gets more and more chaotic. And here, with a moderately large noise levels, it jumps all over the place. But you can see that the endpoints are also still on the data manifold. This is because you're decreasing the noise level slowly, step by step. So the question here is, why do you want to add noise? right? It turns out that for generation, like of data generation, sometimes it could be helpful to add some stochasticity to get more diverse images, as well as in inverse problems, where you want to use diffusion models to solve inverse problems. Adding noise could also be very helpful when you're doing the sampling process. So this kind of provides a way to add noise to this data throughout the sampling process. So this is one way you can improve on the sampling algorithm. Another way to speed up the sampling is some form of so-called acceleration in the process. So this is one a simple update that uses the previous denoiser's outputs to kind of correct for some error made in the current step. And you can see that these trajectories. This is controlled by a parameter gamma, and the gamma here, as you increase the gamma, it kind of becomes more and more aggressive in correction. And you can see that here that samples don't really lie on the spiral, but if you increase the gamma, they tend to the trajectories tend to be less straight and also tend to fall onto the spiral quicker. So there's another way of adding kind of sort of a momentum term, if you want to think about it in this way, to sampling. Yeah. So combining them, combining both of these, you can implement the full sampler in a pretty compact manner. So this code here implements all these different probabilistic and deterministic, as well as the accelerated versions, and in just about 5 lines of code, basically what the equations that I've described just now. So it's controlled by 2 parameters, gamma and mu. Gamma is basically how much acceleration you want to add. So basically, if sampling could take a long time, especially for large models, so you don't want to use too many steps, right? Typically, 10 to 50 steps are what you use. And if you increase gamma, usually you can get similar results with a smaller amount of steps. Mu here is the noise level that you add in probabilistic sampling. If you add a bit more noise, you can kind of increase the diversity of these the samples that you get. And this sampler that we implement here can actually works for a whole variety of pre-trained models, for example, stable diffusion. You get to use this and also modify the sampler in the homework, on real-world models, as well as toy models. All right, so I think this kind of concludes the first lecture. So I basically told you what diffusion models are and how to sample from diffusion models, as well as train them, and kind of the practical considerations that goes into training these diffusion models. And most of this lecture is based on a blog post that I wrote. You can read this for more details. There's also code. The code, this is a library that kind of implements diffusion models in a very simple manner, mainly used for pedagogical purposes and for people who want to experiment with diffusion models and play around with them. So this code will also be used in your homework. And here, so there's many different papers on diffusion models, but I think the most relevant papers to this lecture are these 2, which kind of go through diffusion models from a more practitioner's point of view, looking at what things to tweak in order to get the best results. Different parameters or different settings, both in the training and as well as the architecture considerations for diffusion models. So if you want to train your own diffusion models and figure out how to tune the parameters, reading these two papers could be quite helpful. And in the next lecture, Cole will talk to you more about the inspirations of and perspectives on diffusion models, how we can think about them from different points of view, like say stochastic differential equations, from reversing Brownian motions, from matching flows, and a whole lot of different ways to think about them. So the first lecture, I only talk about practical considerations, but if you want to actually work more with diffusion models, it's actually quite nice to be aware of all of these different interpretations to get inspiration for how to improve diffusion models. So, I think stay tuned for the next lecture. And of course, the PSAT 1, for those who are taking the class for credit, is going to be released today. Watch out for email announcement. And it will be due on Friday. It will just have 2 problems, one more theory and one coding problem. All right, so that's it for today. I'll take any questions. Yeah. Yes?
This is kind of a dumb question, but in the SNR graph, how do you calculate the SNR? Would it just be like the magnitude of the control image?
Yes, so one thing that I didn't, so the question is how do you calculate the signal to noise ratio? Because I've only told you what the noise level is, right? It turns out that this X0 is usually normalized to have unit variance. So because it's normalized, the sigma is basically the noise to signal ratio. Yeah.